All right, so what we have been doing is bivariate graphs. So the scatter plot was looking at our two quantitative variables and plotting a scatter plot with a bunch of dots to see if there was an association, whether these dots lined up. And then we did a cat plot with our categorical variables, both for our explanatory and our response. We had to collapse our response into just two categories so that it would code out and let Python use a mean to calculate the proportion. Proportions are what you use to work with categorical data, and we just had to jerry-rig Python to be able to do that. Then in week 11, we did a very similar thing. We had a categorical as our explanatory, but now we had a quantitative as the response. And so when it did the average for each of the explanatory categories, that was perfect. And so we didn't have to jerry rig anything. We just saw all those bars and saw which categories in the explanatory had a higher or lower average of the quantitative response. So for the next couple of weeks, our Python is going to be pretty easy, but the concepts are going to be much harder. But what we're going to do is one variable hypothesis test. In week 12, this week, we're going to do a z-test for a proportion. So we're going to be working with our categorical variables. And then next week, we'll do a t-test for a mean. And so we'll be working with our quantitative variables. So I'm going to go straight to Python and look at what we've got. And I've brought my Python file down to bare bones. I hardly have anything going on. I have all four variables because I'm going to use the same thing for both this week with the categorical variables and next week with the quantitative. So I've loaded all four of my variables to the file, and I've done the data management for all four of my variables and the formatting for my the formatting for my categorical. But then what I wanted to do, and I kind of had to do it in order to do this week, is I needed to see what the counts were for each of my categories and my categorical variables. So this is super important because what we're going to do is we're going to use our data here in Python as the sample. And so I'm going to go over to my slide right now to show you a little bit what I'm trying to do and then how what I've done here will do that. So I decided to pick the iWhere variable. You could pick either of your categorical variables that you want to, but I picked the iWhere variable. And I looked at this website. I kind of Googled what's the proportion of people who wear glasses or what's the proportion of people who wear contacts. And I found this site, which is right here. And it says that approximately 16.7% of US adults wear contact lenses. Okay, so that piece of information is what I'm referring to when I do my hypothesis test. What I've got is that I think it's a higher proportion because when I look at both category, because they wear contact lenses, and the contact lens category, the total here is like 25% almost a quarter of the people in this sample wear contact lenses. And so I'm thinking that the proportion is actually higher than what was stated in this article. And so that's the hypothesis test I'm going to do. I'm going to see if this sample is enough evidence to support that really the proportion out in the world or out in the country, we'll say, is higher than 16.7%. So that's the hypothesis test that I'm going to try to run. And so how I do that is I have to figure out what the null proportion is. Well, that's just what's in my null hypothesis. And so it's that 16.7%. I have to write it as a decimal. I'm looking to get evidence that it's greater than that. So I put larger here. If it's a right-tailed test, I put larger. If it's a left-tailed test, I put smaller. And if it's a two-tailed test, I forget what I put, so I'm going to look it up. If I just hover over this, it kind of tells me. Let's see. Where is it? Here we go. Two-sided, two-sided is what I do if it's a two-tailed test. So if you ever forget, well, what am I supposed to put there? Larger for the right-tailed test, smaller for the left-tailed test, and two-sided for the two-tailed test. And it's saying alternative because that's the alternative hypothesis. Okay. And again, where did I get that it was a right-tailed test? Here in the alternative hypothesis, we're looking for it greater than the null. Okay, so I have to load or import this particular function from the stats model package. So this is important I could have put it at the very top with these other packages that I loaded, but we're only using it for this particular thing. So I figured I'd just load it right when we need it, right? And then this is the command that will actually do the test. And I need the null proportion. I need whether it's right-tailed, left-tailed, whatever. It's a right-tailed test, so I put larger. And then I need to give it enough information so that it can figure out the sample proportion. And so I gave it the count and the total number of observations. Where did I get that? The count is just the total of 956 plus 308, because there's 956 people who wore both contacts and glasses, so I'm going to count them in the contacts, and then another 308 that just wear contact lenses. So that's the total of these two categories for the count. And then the number of observations, or if you want to say knobs, that's more fun. The knobs is the total of everybody. So I just added all four of these counts together, and that's my total. When it gets the p-hat, it's going to, under the hood, figure out what 1264 divided by 5113 is, right? And it's going to compare that to the 0.167. This stuff is the only output that you get. And before I interpret this, I want to run this same exact z-test on Desmos, because I think it's a little bit easier to see what's going on Desmos. So I'm going to go back to the hypothesis test for proportion calculator. So when I click on that and open up that Desmos file, I actually have coded in here. Like when you're doing yours, you're going to have to change all these numbers, but I have coded in here my null proportion, and that's going to go in the middle of my sampling distribution. It's right here. Then I have my count over my knobs, so this will get my p-hat, which is 0.2472. The sample size, well, that's just how many observations there were, how many people in this sample, that's the 5113. And then this calculates how spread out this sampling distribution should be based on all of that information. And then it figures out a z-score. How many standard deviations above 16.7% is this 24.7%? And I can't even see 0.247 on this screen. It's way over here. 0.215, 0.22, 0.24. There it is. There's p-hat. Way the heck over here. Super, super far in the right tail. So there's not much area out there. And in fact, when it calculates what is the area from that p-hat all the way to infinity, it gets this crazy number, which if you haven't done any algebra in a while, maybe you forget what this minus 40 means. It means 40 decimal place moves to the left. So this is 0.000000000000000. Okay, I'm running out of fingers, right? A lot of zeros before the 1226. Super, 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 just as little as you can think of, way less than the cutoff, which is 0.5. It should be. This is funny. What did I mean here? In this example, the alternative hypothesis is not p is less than 0.5. I think I originally did a different thing. It's greater than 0.167. No. 0. There we go. 167. Okay. Sorry about that. I just noticed that typo and wanted to fix it before I forgot. So anyway, so we only need this p-value, this probability that I randomly pick from this sampling distribution and get something at least as big as my p-hat, right, because it's a right-tailed test. The chances are basically 0. So that we have a lot of evidence. We have significant evidence to say that our alternative hypothesis is probably the case. We have enough evidence to reject. I'm looking for my slide. Where the heck's my slide? We have enough evidence to reject that it's actually greater. The population proportion who wear contact lenses is greater than 16.7%. Okay, so remember, 5%, 0.05, is our cutoff. And if our p-value, which is the second number that Python gives you, is less than 0.05, which this one's way, 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 way less than 0.05, it's basically 0, then we have enough evidence. This number over here is the z-score. It's how many standard deviations away from the assumed mean, the assumed proportion of 16.7%. It's 13 standard deviations away, our p-hat. That's why this proportion, that's why this probability, this p-value is so small. Okay, hope that is helpful. I'm just going to go back to the Python code to show you that this is all they're going to tell us. They're going to give us the z-score and the p-value, and that's it. But that's all you need to be able to say what you need to say about this hypothesis test. Okay, that went a little bit longer than I'd hoped for. Hopefully next week's will be just a bit shorter because a t-test is more or less exactly the same thing. You're just working with means instead of proportions. All right, take care. Bye.